Imagine this. There are things so obvious that we think we never need to think about them again. But then the more closely we look, the deeper we probe, they turn into a puzzle we can't ignore. And for me, that haunting thing began with a scene we've all seen countless times in life. A glass falling to the floor. Crash. Shards flying everywhere. End of story. We treat it as a law of the universe. Natural. Self-evident. No explanation needed. But then, pause for a second and think harder. If I told you to sit down, look at those shards, and wait for them to vibrate, fly back through the air, reassemble into the original glass, and jump back into my hand, you'd think I was crazy. Not just you, all of us. Because in life we've never seen that happen. And strangely, we never even ask why it never happens. Spilled water spreads across the floor, but never gathers itself back into a neat puddle and jumps into the glass. A torn piece of paper turns into scraps, but never spontaneously rejoins. Ocean waves crash against the shore, throwing white foam everywhere, but no one stands waiting for them to reverse into a perfect wall of water and retreat back out to sea. All of these are certainties, powerful, unmistakable, things we never feel the need to question. But this is exactly what frustrates me. Everything in everyday life screams that the world has a clear direction, that you can't go backward, that once something is broken, it's broken forever. Yet when you open a physics textbook and read every line, every equation carefully, you encounter something deeply irritating. Not a single rule of nature forbids time from running backward. No equation states a broken glass cannot become whole again. No line declares water is only allowed to spread, not to gather itself back together. No physical law forces waves to break toward the shore, instead of retreating into the sea. Reality out there is one way, decisive, merciless. But fundamental physics stays silent, and it is precisely in that strange gap between what we observe and what the laws say that the question arises, sharp and challenging. If irreversibility is so obvious, why does physics contain no command whatsoever that the world must behave this way? When we step out of everyday life, where a broken glass stays broken forever, spilled water stays spilled, ocean waves only rush toward the shore and never retreat, and enter the world of fundamental physical laws, you encounter a truth that is almost hard to swallow. None of those obvious things are written into any physics equation, not even the most famous ones humanity has ever discovered. None. Start with Newton's law of gravity, first published in 1687 in Philosophiae Naturalis Principia Mathematica. That equation says gravity is proportional to the product of masses and inversely proportional to the square of distance. But it never says gravity only works when time runs from past to future. If you reverse time in a simulation of Earth's orbit around the sun, 901 seconds, 901 years, or even 901,000 years, the motion still perfectly obeys the law. The elliptical orbit remains an elliptical orbit. There is no arrow of time attached to that equation. Move to electromagnetism. Maxwell's equations, written by James Clerk Maxwell in 1865, are one of science's masterpieces, but they too are time symmetric. If the electric and magnetic fields vary with time t, and you replace t with t, the equations remain exactly the same form. There is no hint that time must go forward. Even at smaller scales, the world of molecules and atoms, things get even more confusing. A molecular collision lasts about half a dozen seconds. If you filmed that event, slowed it down 1,000,000 times, so you could observe every motion, then played the film backward, you wouldn't see anything unphysical. Two molecules approach, change direction, and continue moving, forward or backward. Both are perfectly fine. The Hamilton equations of 1833 or the Lagrange equations of 1788 have no objection to you. Reversing time. I know this sounds insane, but it's true. The fundamental laws of physics are time reversible, time symmetric. Yet when you lift your head from that microscopic world and look at real life, you get slapped in the face by intuition. Life is one way, uncompromising, never turns back. Spilled water spreads, doesn't contract. Cigarette smoke diffuses into the room, never spontaneously returns into the cigarette. An egg falls and shatters. And no, there is no rewind in real life. If you filmed ocean waves at Malibu on a July morning in 2023 and played it backward, I, as a physicist, would have to admit that no equation in classical mechanics, electromagnetism, or quantum mechanics screams that the scene is unphysical. But both you and I know it's wrong. Wrong to the point of being ridiculous. So why? Why does the real world stubbornly insist on no reverse, while every equation we've written, from Newton to Schrödinger, allows time reversal? This isn't just annoying. It poses one of the greatest paradoxes of modern physics. Physics does not demand an arrow of time, yet the real world is bound by it. You could call this the gap between mathematics and reality, between equations and life, between the ideal and our messy world. It's like having a perfect piece of music composed by Mozart in 1783. But when the orchestra performs it, even if they play every single note 100% correctly, the sound lacks one element. The score never specified the direction of time. And that paradox forces us to ask the question any serious physicist must face. If the laws do not dictate the direction of time, then where does that direction come from? Who put it into the universe? And why does reality choose to go in only one direction when the theory allows both? So if all the laws of physics, from Newton in 1687 to Maxwell in 1865, from Hamilton to Schrödinger's equation in 1926, contain no clause whatsoever stating that time must flow forward, then we must accept an important truth. The arrow of time is not in the laws. No equation demands it. No fundamental particle produces it. No one-way principle is written into the basic laws of nature. And this is when you must do what every good physicist does. If a phenomenon is glaringly obvious in reality, but completely absent from theory, look for the cause somewhere else. I often joke with students that if you read a physics book from the first page to the last and still don't find what you're looking for, it's very likely hiding in the spaces between the equations, where nature decides for itself how it will behave. So where does the arrow of time come from? Why does the real world stubbornly operate in only one direction, even though every equation we have allows both? To answer, modern physics offers three main lines of inquiry, each revealing part of the picture. The first direction, statistics of many particle systems. At the molecular level, we're not talking about dozens or hundreds of particles. We're talking about 10, a number so large no human brain can intuitively grasp it. Equations describing the motion of 2 or 3 particles can be beautiful, smooth. But when you put hundreds of billions of particles together, the system no longer behaves like individual elements. It behaves probabilistically, and probability has its own way of operating. It favors what is more likely, more configurations, more arrangements. A single equation cannot describe the collective behavior of an ocean of constantly interacting particles. So even though each individual particle can reverse time perfectly, a system of 10 coarse particles tends to move toward directions with more microstates. And that tendency creates the feeling of one direction in the macroscopic world. But statistics is only the first layer. The second direction, entropy. In the late 19th century, Ludwig Boltzmann produced one of the deepest ideas in physics. He introduced entropy as a measure of the number of ways a system can be arranged to produce the same macroscopic state. Order has very few arrangements. Disorder has countless. This means if you start from an ordered state, like an intact glass or ink sitting in one corner of a tank of water, probability ensures the system will almost certainly drift toward disorder, where there are vastly more possible configurations. No law forces it to go that way. There are simply so many more choices in the disordered direction that it overwhelms everything else. Entropy does not create the arrow of time by compulsion. It only shows that if nature is allowed to choose among trillions upon trillions of possibilities, it will choose the region with more ways to exist, and that is the future. But there is still a third direction. The most important, the initial condition of the universe. When the universe was born about 13.8 billion years ago, it did not begin in chaos, as we often imagine. On the contrary, it was extremely ordered, nearly uniform temperature, nearly uniform matter density, no complex structures like galaxies, stars, or black holes. That initial state had unbelievably low entropy. And this is the key point. If the universe began with low entropy, then from the very first moment, entropy could only increase. And as entropy increases, the arrow of time emerges. Not because of law, but because of the starting point of the entire universe. It is the initial condition that sets the direction of time. So when you ask, why does time only flow forward? Part of the answer lies in the statistics of many particle systems, part in the mathematics of entropy, and part in the moment when the universe was young, hot, and simple. But to see how this picture actually works in everyday life, we need a more visual example. One anyone can imagine without a particle accelerator or telescope ink and water in a glass tank. When you drop a blob of ink into a clear tank of water, the ink does not stay in shape. It spreads, mixes into the water, diffuses into millions of different configurations, and most importantly, it only spreads in that direction. No one has ever seen ink spontaneously gather itself back perfectly. If you understand entropy, you understand why. But before diving into that example in the next part, ask yourself one simple but terrifyingly weighty question for how we understand reality. Is it the gradual increase in disorder rather than the laws themselves that is the true key to creating time? If the answer is yes, then time is not something written in equations. It is the direction nature prefers to go, because that is the direction with the most possibilities. Let's continue with one of the simplest yet most powerful thought experiments that will shake your intuition about the world. The story of ink and water. You don't need a lab, no laser measurement, no equations, just a clear tank of water and one drop of deep blue ink. You release the drop. In the very first moment, it holds a vague shape, a small dense cloud, hovering as if wondering what to do next. But then, almost immediately, it begins to spread. Not fast, not slow, but exactly the way nature always does, gently, steadily, expanding in all directions. After a few seconds, the ink cloud no longer has clear boundaries. After a few minutes, the entire tank has a faint, uniform blue, as if the ink had never been in one specific place. What's interesting? There is no physical law forbidding the reverse from happening. No clause in Newton's mechanics, Maxwell's equations, or Schrodinger's forbids. The ink must spread, or the ink is not allowed to gather itself back into a corner. Physically, it is entirely possible to imagine the film played backward. All the ink molecules leave their disordered positions, move precisely along the reverse paths, collect at a single point, and become the original drop again. No equation objects to that scene. No law forbids it. And that is exactly what forces us to think, why have we never seen it? And not just never seen. Deep in your intuition, you know with certainty, It will not happen. Not once in a million years. Not once in a billion years. Not once in the lifetime of the universe. So what is really happening in that tank of water? To answer, let's imaginatively magnify the microscopic world. Picture every water molecule and every ink molecule the size of a small ball, all of them moving chaotically according to the temperature of the system, hundreds of meters per second for water molecules at room temperature. They collide billions of times per second, bounce in every direction, change velocity, change position, completely indifferent to the original drop of ink you released. When the ink spreads, no molecule decides to spread. There is no force pushing the ink toward disorder. No invisible hand makes it happen. It is all just thermal motion, a chaotic but utterly honest dance of nature. So why does the ink spread? Because there are far more ways to be disordered than ordered. When the ink drop is still intact, the system is in a very special state, a state with very few possible micro-configurations. But when it spreads, the system has trillions upon trillions of different ways to arrange the molecules while still producing a faint blue tank of water. In the microscopic world, where each molecule only knows motion and collision, there is no reason for them to preserve that rare special state. Probability simply does not favor it. If you leave the ink drop in water long enough, the system will always move toward the state with more microstates, and that is the disordered state you observe. This is the first doorway into the true meaning of entropy. You see, entropy is not chaos in the everyday sense. It is the number of microstates corresponding to a given macrostate. And because the uniformly diffused ink state has an enormous number of microstates, while the ink neatly in one corner state has an extremely tiny number, you can understand why the ink drop never returns to its initial state. It would have to pick one very special configuration out of nearly infinite possibilities. No law forbids it. Correct. But this is like expecting to win the lottery 10 times in a row, a number larger than the number of atoms in the observable universe. Not impossible, just never. And this is the turning point. The ink-water experiment gives us the first glimpse of why the macroscopic world has an arrow of time, not because of laws, not because of any mysterious force, but because when you have trillions upon trillions of particles moving according to time-symmetric rules, the overall system leans toward the direction with more possibilities. That is the direction of increasing entropy. In that tank of water, you are not just watching ink diffuse. You are watching time operate. You are watching nature choose the direction with more configurations. And that very choice creates the one-way nature of the world. So what is the next question? If a single drop of ink is enough to reveal the arrow of time, then is the gradual increase of disorder on the scale of the entire universe the deepest key to time? Imagine, and I know this sounds bizarre, that you could enlarge every molecule in that tank of water to the size of a ping pong ball. Nothing else changes. Mass scales with size. Collision speeds correspond. They're just big enough for you to see every impact, every trajectory, every bounce. The entire tank now becomes a gigantic stadium filled with billions of living ping pong balls, moving constantly, pushing, bouncing, spinning, following exactly the Newtonian equations you learned in textbooks. You stand in the center of that stadium, and for the first time in your life, you can observe every microscopic interaction that previously existed only as an abstract concept. What do you see? One very confusing thing. All the collisions you see, every bounce, every path, are completely reversible. If you took that entire scene, every motion of billions of molecules, and played it backward, you would see another version of the same world, and not a single collision would look unphysical. If an ink molecule bounces left because it hit a water molecule, Playing backward, the water molecule bounces right because of the ink molecule. Every velocity, every momentum is perfectly conserved. There is no memory in the laws to distinguish forward from backward. They simply do what the equations tell them to do. Obey conservation of energy and momentum. Nothing more, nothing less. No mysterious magic is broken. No law is inserted to force them to run backward against everyday intuition. At the molecular level, nature knows nothing of the concept of one direction. You could spend all day standing there, watching this magnified molecular stadium, observing trillions of collisions per second, and you would realize this uncomfortable truth. Every single motion is completely reversible. There is no trace saying this is the future, this is the past. No particle decides to spread rather than contract. No bias is written into the laws. But then, when you step back and look at the big picture, the ink still spreads outward, not inward. The water still mixes, doesn't spontaneously unmix. And this is what good physicists must learn to accept. Irreversibility does not come from the laws. It comes from statistics. If you're watching billions of collisions happen, and you reverse them all, you realize this in both directions, forward or backward. Every collision is lawful, but the probability that all those billions of collisions coordinate precisely enough to bring the system from a disordered state back to the original ordered state is so small, it's unimaginable. I often joke that the probability of all the ink molecules spontaneously gathering back to their exact original positions at the exact right time with the exact right velocities is like throwing a piece of bread into the air and having it land as a perfectly wrapped sandwich with the production date clearly printed on it. Not impossible, according to the laws, just so improbable it will never happen in the history of the universe. Now you see the picture. When the ink drop spreads in the tank of water, no particle is doing anything against the law. There is no violation in the microscopic motion. It's just that, and I mean this in the statistical sense, there are thousands of billions of times more disordered states than ordered ones. And because the molecules move randomly, they will easily fall into one of the countless disordered states rather than into one of the extremely rare ordered ones. That is why you never see the ink drop contract back. Not because it can't, but because it almost never happens. This leads to one of the most important revelations of statistical physics. The arrow of time does not come from the fundamental laws. It comes from probability. The molecules are not opposing you. They are simply obeying the mathematics of having more choices. And when the entire universe has far more disordered choices than ordered ones, you get a phenomenon we call time always moving forward. This is the foundation for understanding entropy, and also the key to seeing why the large world is one way while the small world is not. When you've seen each molecule bouncing like gigantic ping-pong balls, every collision obeying conservation of energy and momentum, every tiniest motion completely reversible, you're probably feeling a paradox growing in your head. If everything at the microscopic level is reversible, then why does the macroscopic world, the world you live in, where broken glasses don't reassemble, ink spreads but doesn't contract, refuse to run backward? The answer doesn't lie in the laws, but in probability. And to see that, you must confront the truth that Boltzmann realized over 140 years ago. The number of disordered states overwhelmingly outnumbers the ordered ones. Think of a drop of ink in a tank of water as a simple counting problem. The ink neatly in one place state is one with very few micro-configurations. You can almost point out the position of every molecule. They're in a small region, high concentration, clear shape. But when the ink spreads, the uniformly mixed water state corresponds to a huge number of configurations, trillions upon trillions of different arrangements that your eyes can't distinguish. This is the key point. Nature doesn't prefer disorder. Nature just tends to fall into where there are more choices, and the disordered region has a number of choices, incomparably larger than ordered. That's the difference between a single lonely path and a highway with millions of exits. Now imagine you randomly pick a point on a map. The chance of landing exactly on that lonely path is near zero. The chance of landing on the highway is almost certain. When trillions of molecules move randomly, the system doesn't choose disorder because it likes disorder. It falls into disorder because that's where most of the landing spots are. That's the mathematics of probability, not the philosophy of chaos. From this perspective, the disordered state isn't a destination, but the widest region in the space of possibilities. The ordered state is just a tiny corner, narrow like a crack in the massive wall of a quadrillion choices. This is why ink spreads in water. No force needed, no rule needed, just probability. But the most important thing is this: the process of ink spreading is physically consistent, and the process of ink spontaneously gathering is also physically consistent. Both obey the laws. The difference lies in probability. For the ink to spontaneously gather, every ink and water molecule must move along the reverse path with extreme precision to the point where the probability of that event is less than 1 in 10, circumflex 10 circumflex 23. That's not just an unbelievable number. It's larger than the number of atoms in the entire observable universe. This is like expecting all the air molecules in the room to spontaneously concentrate in a small corner, suffocating you. No law forbids it, but you don't worry, because the probability is so small that nature never draws the winning ticket. When you understand probability, you start to see something more profound. Time isn't a flow. Time is the direction where the number of possible states increases. Think about how our language reflects this intuition. When you say things progress, what you're really saying is the system moves from few states to many states. When you say everything gets messed up, you're describing the process of entropy increasing. When you say you can't go back to how it was, you're describing the fact that the initial state has very few ways to exist, so the chance of returning is zero. In the physical world, the future is precisely the region with more possible states than the past. The past is those special rare states with so few configurations that nature only passes through them once and leaves them forever. And this is what makes time one way. Nature always moves from states with few configurations to states with many configurations, not because laws require it, but because probability overwhelms to the point of being irresistible. The disparity between the ordered region and the disordered region is so vast that it creates the sensation of time flowing, when what's really flowing is just the system advancing into regions with more choices. From here, a serious question arises. If time is just the direction of probability, then isn't all the irreversibility we experience, from broken glasses to disintegrating stars, simply the result of nature always choosing the region with more possibilities? And if so, what happens when we apply this perspective to a larger scale, to the entire universe? When you've understood that irreversibility comes not from the laws, but from probability, you'll start to see why I often say this to my students. It's not impossible. It's just never going to happen. That's the simplest way to describe a subtle truth that statistical physics has been trying to teach us for over a century. Nature could make everything run backward, but to do so, it would have to perform a feat of precision so utterly unrealistic. Let's go back to the drop of ink in water. If you rewind time, in terms of laws, every reversed motion is valid. The molecules just flip the sign of their velocity and retrace their exact paths. But for all those thousands of trillions of molecules to simultaneously follow that perfect reversal in the real world, no extra collisions, no motion off by 1,000th of a second, You're asking nature to perform the equivalent of winning the jackpot of every lottery that ever existed, all at once, continuously, throughout the lifetime of the universe. And worse, if just one molecule messes up the script, if just one has an error, no matter how tiny, the entire process collapses immediately. That's what I call practically impossible, in principle allowed, but in practice never under any circumstances happening. Not because laws forbid it, but because the number of conditions needed to precisely reverse time at the microscopic level exceeds anything nature is capable of. Think of it this way. To bring back the past, nature doesn't just need to return the system to the initial state. It needs to return it to one of the extremely few micro-configurations that make up that initial state. Meanwhile, the current state, disordered, spread out, mixed, has so many configurations that if you tried to write that number on paper, the number of digits would be larger than the number of atoms in the observable universe. That is, nature is playing a game of finding one single key in a space so vast, it's unimaginable. This is why saying ink never spontaneously gathers isn't a philosophical statement. It's a mathematical one. The probability of it happening is so small that if you simulated the universe running for 10 circumflex, 100 years, you still wouldn't see it. And this isn't just true for ink. It's true for everything in life. Cigarette smoke doesn't spontaneously return to the cigarette. A billiard table doesn't spontaneously rearrange into a perfect formation. An egg doesn't spontaneously mend. Those things aren't against the laws. They're just too deep in the practically impossible region. When you view the world through this lens, the arrow of time, which Newton, Maxwell, or Schrödinger never wrote into their equations, suddenly becomes much easier to understand. Time has a direction, not because nature prefers one way over the other, but because the random motion of particles always leads the system into the region with more configurations, and away from the region with fewer. That's unavoidable. That's statistical inevitability. If you imagine the possibility space of a system like the terrain of a gigantic valley, where the disordered region is the vast lowlands with millions of paths, and the ordered region is a tiny, lofty, slippery peak, then nature always falls into the lower, wider region, not because of gravity, but because of probability. And when nature always falls toward the region with more configurations, that direction is what we call the future. The past, with its tiny and special number of configurations, becomes something we can only pass through once. This leads us to an important realization. The arrow of time isn't a physical object. It's the statistical inevitable consequence of large systems. And if the arrow of time is just the bias toward more possibilities, then the next question becomes clear. When we say time flows, are we really talking about time, or are we just talking about entropy? I want you to forget the textbook formulas for a moment. Here we don't need S equals sine K log W or any expression. We just need intuition, a way to see life like a physicist, but without losing the simplicity of everyday life. Imagine you walk into a messy room, clothes strewn everywhere, books fallen off shelves, papers scattered like a gust of wind just blew through. Now imagine that room perfectly tidy, shirts folded, books neatly stacked, desk spotless. What differs between these two states? At a very deep level, the answer is the messy state has far more ways to exist than the tidy one. There are millions of ways for the room to become cluttered. Just toss a book out of place, forget a shirt, drop a few papers. But for the room to be tidy, everything must be in its exact spot, meaning the number of valid configurations for clean room is very few, while the number for messy room is nearly infinite. That's entropy, not emotional chaos, not a mental state, not anything mystical, but the number of ways a system can be arranged. The more ways, the higher the entropy. The fewer ways, the lower the entropy. Now go back to the drop of ink in water, or the molecules you've magnified to ping-pong ball size. The ink contracted in a corner state is equivalent to an extremely tidy room. There are only very few ways to arrange the molecules to keep that special shape. The uniformly spread ink state is like the messy room. There are trillions upon trillions of configurations that create that image. When the system moves randomly, it doesn't choose disorder, but simply whatever. And whatever means going into the region with the most possibilities. That's why entropy always increases in the real world, because microscopic motion has no goal. And in the gigantic space of possible states, the system is almost certain to fall into the region with more configurations than the one with fewer. This isn't a law forbidding reverse flow, but a law about tendency. A round ball placed on an inclined plane isn't forbidden from rolling uphill. It rolls downhill because there are more positions below than at its initial position above. Entropy is similar. The system isn't forbidden from decreasing entropy. The probability of it doing so is just so small that nature never manages it. So what does increasing entropy mean? It means the past of a system is always in a more special state than the present, meaning the initial state is always fewer configurations, and as the system progresses, the number of possible configurations it can fall into expands like an endless field. We feel this in every aspect of life without thinking about physics. When you drop a glass and it shatters, the number of states the shards can occupy on the floor is countless times more than the states of the intact glass. When you stir sugar into your morning coffee, you don't need a law to believe the sugar will dissolve evenly, because the undissolved sugar state has very few micro configurations, while the evenly dissolved sugar state has so many that the system can hardly avoid it. When you live another day, your house, your body, even your memories evolve toward increasing possible states. Complexity grows. Randomness touches everything. That's entropy. But the most beautiful thing here is entropy isn't a force, doesn't push or pull you anywhere. It's just a property of the number of possibilities. And when you understand this, the arrow of time becomes astonishingly clear. Time is the direction where the number of micro configurations increases the fastest. Time flows not because clocks run. Clocks run because time flows. And time flows not because the universe commands it, but because in the gigantic space of every state, molecules can occupy. Nature almost always goes into the region with more choices. That's why entropy always increases in the real world. Not because laws compel it, but because the mathematics of probability makes every rare state, those with low order, almost never repeated. And from here a deeper question arises. If entropy is the measure of the number of possibilities, then what determines the initial possibilities of the universe? When you've grasped that entropy increases not because of some pushing force, but because the number of possible configurations of the system keeps growing larger, an interesting question begins to emerge. If the initial ordered state is special and rare, and the system quickly plunges into a gigantic ocean of disorder, does the past disappear? The answer, surprisingly but extremely important for how we understand time, is no. The past does not disappear. It is encoded into the present configuration. When a system moves from order to disorder, it does not forget the past. It only makes information about the past much harder to access, like a voice drowned out in a noisy room. This is where statistical physics and quantum mechanics meet to deliver one of the deepest truths. Information never disappears. It only spreads, diffuses, becomes buried under countless microscopic details, to the point that you, as a coarse-grained observer, can no longer gather those traces back together. Go back to the messy room in the earlier example. A clean room actually contains far less information than you think. Everything is in its exact place. Everything is clearly positioned, and it can be described with very little data. But when the room becomes messy, the information doesn't decrease. It increases, but it increases in complexity. Each item is slightly out of place compared to before. And if you want to reconstruct the original state, you need to remember a myriad of tiny details. The angle of the book, the few centimeter offset of the shirt, the new creases that appeared from collisions. When the system becomes disordered, information about the previous state is not erased. It is merely scattered into billions of minute changes, each change holding a piece of the original story. And because you cannot observe every single microscopic particle, you lose the ability to recreate the past. But that does not mean the past vanishes. It simply becomes deeply hidden. Apply this to the ink in water tank. An initial drop of ink is an object with clear structure, defined boundaries, distinct shape. When it diffuses, you see a uniform faint blue. But in reality, that blue is not a new simple state. It is a collection of an enormous number of extremely complex microstates, each ink molecule in a different position, mixed with different water molecules, having collided along distinct histories. All those collisions still contain information about what happened. To recreate the original drop of ink, you would have to reverse not only the path of every single molecule, but also every collision they had with trillions of others. That information is still there, recorded in the position and velocity of every particle. It's just that you cannot read it. It is like burning a sheet of paper. You think the information is destroyed, but at the molecular level, the information about the original text is pushed into the state of the gas molecules, light, heat, and soot. It is not lost, only dispersed. That is precisely what Stephen Hawking had to confront in the black hole information paradox. If information really disappeared, all of quantum physics would collapse. And because physics does not collapse, we know information cannot disappear. It can only become unrecognizable. This is the foundation for saying that the past does not disappear. When I say that, I am not speaking poetically. I am speaking physically. Every present state is the result of trillions of previous interactions, and all those interactions leave traces in the microscopic configuration. You may not be able to find those traces, reconstruct them, or read them, but they are still there. This is also why you cannot go back to the past by reversing time. To do so, you would have to recreate the entire original information, including every microscopic motion of every molecule. You cannot do that. But the universe already did, because it always carries everything with it. We just cannot decode it. And when you understand this, a deeper picture of time emerges. Time does not erase the past. Time only makes the past spread wider, encoded in details, so fine they cannot be gathered again. Where is the pause? Located in the universe. If information is never erased, where does it reside? And how can the universe, with its apparently chaotic operation, preserve traces of every event that ever happened? To understand this, you must see the universe as a gigantic memory, not the kind with drawers, hard drives, or folders like a computer, but a distributed memory where every tiny interaction between particles leaves a microscopic imprint in the configuration of the entire system. Start with something extremely familiar. Photons. Every photon your eyes receive is a piece of information from the past. When you look at a star 1,000 light years away, you are not seeing the star as it is now. You are looking at photons that left it around the year 1024, when Earth was still in the Middle Ages, when Newton had not yet been born, when there were no telescopes. Those photons carried information about the star's position, temperature, and gas composition at that time, and traveled straight to your retina. A photon emitted from the Andromeda galaxy, 2.5 million light years away, is a video recording of 2.5 million years ago, when our human ancestors had not yet appeared. The universe stores the past in light, and there is no way for a photon to forget where it came from. Its path, its energy, its direction all encode information about the event that created it. But photons are just a simple example. Go deeper, to smaller scales, air molecules. Right now, in the room you are sitting in, every air molecule collides with about n-half other molecules every second, and every single collision leaves a tiny change in velocity, in direction of motion, in the energy of both molecules. This means every molecule in the room is carrying imprints of the past, of every previous collision, and through them, of the entire aerodynamic history around you. If a table was dragged across the floor at 8 a.m., the air molecules that hit the edge of the table as it moved carry a trace of that motion. You cannot read it, but nature carries it forever. I like this metaphor. Imagine the universe is a gigantic drum. Every event in the universe, a molecular collision, light from a star, an object falling to the ground, is a beat struck on that drumhead, and the drumhead vibrates, spreading ripples in all directions. Even if you can no longer hear the original sound, the microscopic vibrations remain in the current configuration of the drumhead. They do not disappear. They just blend into billions of other vibrations. The universe operates that way. Every light, every push, every touch is a beat on the fabric of space-time, and its echo, though it fades, never completely leaves the system. But there is another metaphor I think is even more intuitive. The universe is like a gigantic block of snow, where every snowflake carries its own unique structure, formed from past temperature and humidity conditions. No two snowflakes are alike, and no two molecules in the universe share the same history. Each molecule is a distorted, noisy recording, but it always exists. When ink spreads in water, information about its initial state remains stored in the position and velocity of every ink molecule. When a glass shatters, information about its original shape is still there, controlled by energy, fracture direction, trajectory of each shard, and each dust particle. Even when a star explodes in a supernova, information about its initial state is dispersed into radiation, plasma, and gravitational waves, spreading across the universe. There is no way to delete information. Nature provides no delete command. So when you ask, where is the past? The answer is everywhere. In the light coming from distant galaxies, in the moving air currents around you, in the smallest structures of matter, in temperature, in waves, in the distribution patterns of particles you cannot see. The universe is a distributed memory, so thorough that when you look at any present state, you are looking at the result of every event that ever happened in the history of the system. Not fully retrievable, but always present. When you realize that the past is encoded in the present and never truly disappears, you find yourself facing again a paradox that has been lurking. How can entropy keep increasing relentlessly while every fundamental law of nature is completely time reversible? This is where the two crucial pieces of the puzzle, the time symmetry of the laws and the statistical tendency of many particle systems, fit together so tightly it's almost headache-inducing. At the microscopic level, as you've seen, if we reverse the velocities of every molecule in a system, their motion would be perfectly legal, according to every known physical law. Newton doesn't object. Maxwell doesn't object. Schrödinger doesn't object. Even Einstein's general relativity, which is extremely sensitive to the structure of space-time, contains no clause forcing time to run in only one direction. Yet at the macroscopic level, entropy increases as though it were an absolute law. Ink spreads but doesn't contract. Heat flows from hot to cold, never the reverse. Glasses break, but don't reassemble. All familiar phenomena behave as though nature hates reversal. You know every microscopic motion is reversible. You also know every macroscopic process is irreversible. These two truths coexist, and if you don't see the paradox here, you haven't looked deeply enough. The funny thing is that the physical equations themselves are almost eerily neutral. They do not supply an arrow of time. They only describe how the system evolves in either direction. So where does the arrow of time come from? From entropy, but not in the sense that entropy is written into the laws, but in the sense that entropy emerges as an unavoidable statistical consequence of large systems. Think of it with this metaphor. You drop a stone into a lake. Ripples spread outward. Every equation describing surface waves allows the ripples to run backward, contracting back to the center. But that never happens. Not because the laws forbid it, but because the number of ways for the disordered oscillations to precisely reassemble into the original neat pattern is so small it never occurs. The same is true for entropy. The arrow of time does not come from fundamental laws. It comes from the asymmetry in initial conditions and the way statistics governs the evolution of the system. The laws are neutral, but the universe did not begin in a neutral state. It began in a state of extremely low entropy. That is the root of everything. And this is where we come close to cosmology, because the real big question behind the arrow of time is not why does entropy increase, but why was the initial entropy of the universe so absurdly low? If the universe had begun in the most disordered state possible, we would have no arrow of time, no past, present, future, no distinction between events that have happened and events yet to happen, no order to lose, no structure to form. But the universe did not begin that way. Instead, according to observations from the WMAP satellite, 2001, 2010, and later, Planck 2013, 2018, the early universe was extremely uniform, matter density almost identical everywhere, temperature fluctuating by only about 1 part in 100,000, a smooth state so smooth that compared to any physical system around us, it is a state of very low entropy. In the gravitational world, uniformity equals sign order. True disorder is when matter clumps into stars, galaxies, black holes, extremely complex structures. That means the entropy of the universe increases not because laws demand it, but because the universe began in a state that requires increase. The arrow of time exists not because equations have direction, but because the universe had direction in its very beginning. This is the final piece that connects everything we've said. The laws of physics allow reversal statistics drive systems from few configurations to many, but that only produces an arrow of time if the initial state has low entropy, and that is exactly what happened. Entropy increases even though the laws are reversible. If you want to understand where time really comes from, why past differs from future, why we remember but do not foresee, why things break but don't reassemble, you must look at the very early universe. This is where the arrow of time was set, not by a law, but by a special beginning, so exceptional that everything afterward had to unfold in the direction of increasing entropy. To understand this, imagine you walk into a kitchen early in the morning. You see sifted flour, eggs already cracked in a bowl, the oven preheated, everything perfectly arranged, so that you only need a few steps to create a cake. That kitchen is in a high order state. The remaining possibility space is vast, And most possibilities lead to disorder. Spilled flour, dropped eggs, incorrectly mixed batter. But the key point is, the kitchen was initially arranged, and that very arrangement opens the future of the cake. The early universe was the same. It began in a smooth, uniform, structureless state, a state where matter density fluctuated by only 1 part in 100,000, as confirmed by Kolbe, WMAP, and Planck measurements over 3 decades. This smooth state, to everyday intuition, sounds like disorder. No shape, no order, just a uniform sea of plasma. But from the perspective of gravity, uniformity is equivalent to order, because the high entropy state in the universe is not smooth but clumped stars, galaxies, and ultimately black holes. Roger Penrose, one of the greatest mathematical physicists of the 20th century, emphasized that a universe full of black holes would truly be a high entropy universe. Yet right after the Big Bang, there were none. Conclusion: the universe began in a state of unbelievably low entropy. To grasp how special this state was, imagine you have a deck of Henthetheth cards, roughly the number of atoms in the observable universe. Shuffle it until it randomly falls into perfect order from ace to king in all 4 suits. The probability is almost 0, but not exactly 0. And that is exactly how rare the initial state of the universe was. Nothing in the laws forced it to begin that way. It simply did. Now imagine the difference if the universe had started in a high entropy state. If matter were distributed chaotically, clumped, full of black holes from the beginning, random motion would not produce an arrow of time. Disorder would already be maximal, with no direction left to increase. No stars would form. No galaxies would clump. No large structures. No chemistry. No life. And most importantly, no past and future in the sense we understand. The arrow of time exists only because the universe began at low entropy, allowing entropy to increase over billions of years. That is the one necessary condition for everything to evolve. From fundamental particle, atom, stars, planet, organic molecule, living things, humans, civilization. All of it is cracks, gradually appearing as entropy rises, like delicate patterns spreading across a cold pane of glass when vapor begins to condense. To make it clearer, I want to use another metaphor. Imagine a gigantic stadium. All the spectators are standing in perfect rows, every line aligned, no one out of place, perfect order. Now imagine they start moving randomly in every direction. Very quickly, the clean formation disappears, replaced by complete chaos. Now if you ask, why doesn't the formation spontaneously return to how it was? The answer lies in probability. But the more important question is, why was the initial formation so orderly? And the answer for the universe is, we don't know. But we do know one thing. That extremely ordered state is the cause of the arrow of time. It is why the past exists. It is why the future differs from the past. It is the foundation for all the irreversibility you see around you. From ink spreading in water to glass shattering. From life emerging to stars dying. Everything evolves in the direction of increasing entropy. And that direction exists only because the universe began from a point of unexpectedly low entropy. The universe began in such a low-order state that it set the arrow of time in place. But there is an even deeper question waiting for you to confront. Why can information about the past never disappear? If everything spreads, mixes, increases, entropy becomes more disordered over time, why can we still say that the past is encoded in the present state? Why doesn't it dissolve into nothingness? The answer lies in one of the foundational principles of physics that you sometimes hear, but may not fully appreciate: conservation of information. This principle is not a philosophical slogan. It is one of the bedrock blocks of both quantum mechanics and classical mechanics. In every physical interaction, molecular collisions, heat radiation, chaotic motion, information about the initial state is not erased. It is only spread out, distributed across countless tiny degrees of freedom, to the point that it cannot be recovered by any practical means. In other words, nature has no delete button. Every collision between two air molecules, every photon emitted from a hot surface, every tiny vibration in a crystal is a transformation that preserves all information from the previous state, but re-encodes it into a new microscopic configuration. In quantum mechanics, this is expressed by unitarity. The evolution of a quantum state is like stirring a glass of water. No matter how long you stir, no molecule disappears. They only change position. And if you had enough microscopic data, which humans never have, you could perfectly reverse the process. In practice, you cannot, but nature still keeps all the information. Imagine you write letters on the still surface of a lake with a long stick. The water edge is pushed out, creating ripples. After a few seconds, the letters disappear. But the waves continue to spread, break into smaller ones, interfere with each other, carrying energy and information across the entire lake surface. The letters are no longer there, but the information about the motion has merged into countless tiny ripples. If you had a magical machine that could measure every water molecule and its velocity, you could reconstruct the letters you wrote. That is conservation of information. Similarly, when a glass shatters, you see loss of order, but at the molecular level, all information about shape, structure, energy, and impact direction is distributed into the velocities of the shards, sound waves in the air, vibrations of the floor, heat generated by friction. Nothing is lost. The information has simply become so dispersed that recovering it would require describing the state of 10 particles, something no brain, no computer in the universe could do. The past's information, therefore, never dies. It hides in the gigantic microscopic configuration of reality. Imagine the past as a crystal wine glass falling onto a stone floor. That sound, that vibration, those shards, everything is the universe recording the event. Sound waves propagate, spread, vibrate billions more air molecules, each hitting the next, creating a chain that carries information far beyond your sensory range. Some energy turns into heat, increasing the microscopic velocities of surface floor molecules. That too is information. Some energy produces weak electromagnetic waves. That too is information. But because all those signals spread to the point they cannot be gathered, you feel as though the information disappeared. In reality, it has only dissolved into the vast structure of the world, like a drop of ink dissolving into the ocean. Never lost, only irretrievable. This is also why the black hole information paradox caused physicists headaches for 40 years. If information could disappear in a black hole, all of quantum mechanics would collapse. But because information is never allowed to be lost, we now believe Hawking radiation must carry the information that fell into the black hole, even though the exact mechanism is still being unraveled. That only reinforces the truth. Nature does not destroy information. It only re-encodes it in ever more complex ways. In everyday life, you feel loss. You think an event that has passed is gone. But on the physical level, the past still exists. Not in a form you can access, but as a scattered record divided across countless micro-states that human eyes cannot distinguish. And precisely because information never disappears, entropy has meaning. It does not count chaos. It counts the number of ways past information can be dispersed while still being preserved. If you want to know why the past cannot be erased, why every attempt to turn back time fails, and why the universe behaves like an absolutely perfect recording machine that never allows the tape to be erased, then this is exactly where the answer lies. Neatly, unitarity, the unitarity of quantum evolution. And don't worry, I'm not going to throw a bunch of curly equations at you. Let me explain it in exactly the style I like best. simple, intuitive, and fun. In quantum mechanics, the state of a system isn't it's here or it's there. It's a collection of possibilities wrapped up in what we call the wave function. Imagine you're listening to a choir. Each voice is one possibility, and the wave function is the musical score that contains all those voices together. When the system evolves over time, what unitarity guarantees is this: no voice ever disappears. No possibility is ever deleted from the score. Everything just changes the way it blends together. That's why I often tell my students, in quantum mechanics, nature is a magical pianist. He can play the piece in a new way, but he never drops a single note. Unitarity means the evolution of the wave function always preserves the total information of the system. There is no delete button in the quantum world. No whiteout, no start over from scratch. Everything only changes shape. Just like you can mold clay into different figures, but never naturally lose any of the clay itself. Here's a simple example. Imagine two molecules interacting. Before the interaction, the system has a certain wave function. After they collide, the state changes. Different velocities, different positions, different directions. But if you know the final state perfectly, unitarity says you can, in principle, calculate backward to the initial state, not with the naked eye, not with a computer, but in principle. Nature remembers everything, every quantum interaction. No matter how small you can't feel it, is a linear transformation that conserves information. Even when you observe a system and the wave function collapses, that doesn't destroy information. It only transfers the information into the state of the system, plus the measuring device, plus the environment. The information isn't lost. It just changes address, like writing a letter to a friend. But instead of sending it to one person, you send millions of blurry copies, flying all over the room. And yes, that sounds messy, but it's still conservation of information. Another example I love. Imagine a perfect billiard table. You strike one ball, it hits another, then another, spreading across the table. After 30 seconds, if you look at the table, you can't possibly know exactly what the initial shot was. But the billiard table knows. It knows through the microscopic positions of every ball, the spin on their surfaces, the energy dissipated as vibrations in the table. The information isn't erased. It has simply become too intricate for you to access. Quantum mechanics takes that argument to a deeper level. Not only does the macroscopic world remember the past in a tangled way, but the microscopic states themselves cannot destroy information. This is exactly what made the black hole problem such a massive shock to physics in the 1970s. Stephen Hawking argued that information could actually disappear when it falls into a black hole. But if that were true, all of quantum mechanics would collapse because unitarity would be violated. That's why, for decades, leading theoretical physicists like Leonard Susskind, Gerard Hooft, and many others fought to defend this. Information cannot disappear, even in a black hole. And recent progress supports that view. Hawking radiation cannot be completely random. It must carry encoded information about what fell in. It doesn't matter exactly how it encodes it. What matters is that nature cannot allow information to be erased. All of this leads to a very important realization. The deepest reason the past cannot disappear comes not only from statistics, not only from entropy, but from the quantum nature of the universe. A universe where every evolution preserves all the original information, but hides it in countless tiny degrees of freedom. Imagine reality as a tapestry woven from millions of threads. You can change the pattern. Pull this thread left, push that thread right, add new designs. But you cannot erase a thread that has already been woven in. You can only make it blend into the others until the naked eye no longer recognizes it. That is unitarity. And when unitarity is the foundation of every motion, you can see why the past is never erased. It cannot be erased. It only becomes hard to access, hard to recognize, hard to separate. And if unitarity in quantum mechanics is the assertion that information is never erased, then black holes, those gravitational monsters predicted by Einstein and observed many decades later, appeared as a gigantic challenge, almost a declaration. Let's see if your rules are really true. A black hole is a place where everything that falls in is compressed until there is no escape, a region of space-time where even light cannot cross the event horizon. If you wanted to hide information, destroy structure, or burn away every trace of the past, a black hole sounds like the perfect candidate. Then, in 1974, Stephen Hawking did what physicists love most. He looked at an idea that seemed perfect and found where it cracked, using quantum mechanics to analyze quantum fields near the event horizon. He discovered that black holes are not completely black. They emit radiation, now called Hawking radiation, and gradually evaporate over time. That means if you throw a book into a black hole and wait long enough, the black hole will radiate and eventually disappear. A small but extremely troubling problem immediately arose. Where does the information of the book go? Hawking originally argued that it disappears, and that claim caused an earthquake in physics. If information can be destroyed in a black hole, quantum mechanics is no longer correct. Unitarity is violated. The entire beautiful mathematical foundation of quantum mechanics collapses. This made the world's leading theoretical physicists stand up in opposition. Most notably Leonard Susskind, who opened a decades-long intellectual war with Hawking to defend the principle of information conservation. That war became so famous, they called it the Black Hole War. And the deepest reason was simple. The laws of quantum mechanics say information cannot disappear, no matter what you do to it. You can burn the book, crush it, dissolve it, but its information goes into the state of the gas molecules, the heat, the light, and never simply ceases to exist. Therefore, if black holes destroy information, they break a mathematical structure that all modern physics rests upon. So black holes became the perfect testing ground to ask if nature truly cannot erase information. Does it have any way to escape this paradox? The answer came from a series of discoveries in the 1990s and 2000s. The holographic principle, ADS-CFT correspondence, and deeper studies of quantum gravity all pointed to the fact that Hawking radiation cannot be completely random. It must carry information about what fell into the black hole, but encoded at an unbelievably sophisticated level. Picture this. You throw a letter into a fire. The fire turns the letter into ash, gas, and light. You think the information is gone, but if you could measure every photon of light emitted, every gas molecule rising, every tiny vibration of the air, you could reconstruct the letter. In practice, you can't. But nature does not allow information to be erased. Black holes do the same thing, but in the most extreme version, nature can create. And this truth reinforces what we've been chasing since part 8. Information does not disappear, not in ink-diffusing water, not in air, not in molecules, not in quantum mechanics, and certainly not in black holes. This is nature's great failure. Not failure in the sense of being wrong, but failure in the sense that it cannot break the principle of information conservation, even in the most extreme circumstances. Every past, every event, every interaction leaves a trace that the universe is forced to carry, even if it is crushed, melted, or thrown into the heart of a black hole, millions of times more massive than the sun. So if information never disappears, not in ink-diffusing water, not in molecular motion, not in quantum mechanics, not even in black holes, then why can't we access the past again? Why can't we rewind reality, like rewinding a movie? Why can we only remember in one direction, look in one direction, live in the direction of increasing entropy, without ever returning to the starting point? The answer lies in a simple but brutal truth. Entropy dilutes information to the point where it cannot be recovered, even though it still exists in every microscopic detail of the universe. Go back to the image of a drop of ink falling into a tank of water. As it spreads, information about its initial position does not disappear. It diffuses into the velocities of every water molecule, every random collision, every tiny trajectory. To access the past again, you would have to measure all those molecules with perfect accuracy, position to within a part in 10 tankard meters, velocity to within a part in 10 tankard seconds. Not just a few molecules, not just millions. You would have to access the exact state of 10 tankard particles, each carrying a tiny piece of the original story. And if even one of those particles is off by the tiniest amount, just one, the entire reversal process collapses completely. Not 90% failure, not 99%, but 100%. This is not a technological problem. It is a matter of principle. In the real world, there is no device, no computer, no artificial intelligence, no civilization, even a hypothetical civilization capable of harnessing the energy of an entire galaxy that can measure the exact state of every particle in a large system. And even if they could measure it, they would still have to control every single particle so that all of them reverse perfectly at the same time. That is the most unrealistic demand ever posed in physics. Entropy increasing means information becomes more and more spread across more degrees of freedom, just like shouting into a vast cavern, and the echo scatters in millions of directions. The sound doesn't disappear, but it cannot be gathered back to recreate the original words. The past is the same. It doesn't vanish. It simply becomes a chaotic harmony of countless elements you cannot separate. Imagine you write a sentence in the sand on a beach. A wave washes over it. Sand grains are displaced, pushed, rolled away. Information about the original sentence is still there in the position and collisions of every grain of sand. But if you want to read that sentence again, you must know exactly where every grain is, how much every grain has moved, which grain hit which, and not just the sand grains, but also the water molecules that pushed them, the air molecules that swirled past them, the sunlight photons that shone on them. The past is written into the microscopic structure, but reading that structure back is an impossible task. This is the profound reason humans can only remember and cannot go back. Entropy spreads the past into countless details, to the point that no brain, no observer, no measurement system can ever reassemble it. When we say time flows, what we actually feel is the relentless increase in the number of possible states, and that number is so large that the past is diluted like a drop of ink in the ocean. It is there, but it dissolves into the structure of the universe, irretrievable, irreversible, inaccessible. And this is the crucial point many people misunderstand. Does not disappear, does not mean can be accessed. A book that is burned does not lose its information, but you also cannot read it again from the ashes. A shattered glass still contains all the information about its original shape, but you cannot reassemble it by measuring the motion of every molecule in the air. Likewise, the universe contains its entire history in the present state, but no one, no thing can decode it back into a living sequence of events. We cannot return to the past, because doing so would require reversing entropy, gathering information that has been scattered into 10 conch pieces, and placing every molecule back in its exact original position. That is not against the laws. It is just so improbable that it is smaller than the chance of you throwing a stone into the air and having it land as a perfect statue of David. Thus, the one-way nature of time is not enforced by any law, but by the reality that the microscopic details that make up the past are spread too widely for any intelligence to gather them back together. If entropy is the reason we cannot access the past again, then to feel the power of this principle in a more intimate and intuitive way, there is no better example than the ratchet mechanism, the pawl and ratchet wheel that I always loved using to explain the nature of irreversibility. Imagine you have a small wheel with saw-like teeth, just like on a wrench. A pawl presses against those teeth with a spring. When the wheel turns in one direction, the pawl lifts and drops, allowing the wheel to continue turning. But when the wheel tries to turn backward, the pawl catches in the teeth and completely blocks the motion. At first glance, you would think this is the perfect irreversible machine. The wheel only turns one way. No reversing possible. Mechanical one-way time right in front of you. But as always, nature is never as simple as its surface appearance. I want you to connect that ratchet to a small vein. Place it inside a box full of gas, where air molecules randomly bombard the vein due to thermal motion. You might think, perfect. The molecules hit the vein, push the wheel to turn, and because the pawl blocks the reverse direction, the wheel will keep turning forever in one direction, a form of perpetual motion. But then we run into trouble. Thermal motion itself prevents this machine from working. When the ratchet turns, the pawl lifts and falls. Friction generates heat. The pawl heats up, and when the pawl becomes hotter than the vein, the thermal motion of the pawl itself starts making it jiggle, randomly popping off the teeth at unpredictable moments. This allows the wheel to turn in the reverse direction. What was just blocked gets liberated by heat. Then nature finishes the job. If both parts are at the same temperature, random motion will drive the wheel to turn in both directions with equal probability. Result: irreversibility disappears. The machine only works one way when there is a temperature difference between the two parts. If the vein is hotter than the pawl, the wheel turns one way. If the pawl is hotter than the vein, the wheel turns the opposite way. No difference, no direction. This is a profound lesson. Irreversibility, the arrow of time, does not arise spontaneously from the mechanism, from force, or from the structure of the machine. It comes from entropy, from a temperature gradient, from a difference between two states that have different numbers of configurations. If the two parts of the system have the same entropy, the system loses its arrow of time. If there is an entropy gradient, the system has direction. Everything in the ratchet machine is described by the fundamental laws and is reversible. Every collision between a molecule and the vein, every lift of the pawl, every tiny oscillation in the spring, all obey Newton's mechanics and can in principle be reversed. But the overall system is not reversible unless there is an entropy difference. That exactly mirrors the macroscopic world. Without entropy, there is no arrow of time. Imagine this through a more familiar metaphor. You have two glasses of water, one hot, one cold. Heat flows from hot to cold, never the reverse. But why? Not because of any mysterious force forcing heat to go one way, but because the state, both glasses at the same temperature, has vastly more micro configurations than the state, one hot, one cold. When the two glasses reach thermal equilibrium, entropy reaches its maximum, and the arrow of time disappears. No spontaneous process occurs anymore. The ratchet machine perfectly simulates this logic. It only turns one way when there is an entropy difference. When the gradient disappears, time in the dynamical sense stops. Now connect this to everything we've seen about black holes, about ink spreading in water, about the air in your room, about molecular collisions, and about quantum evolution. Wherever there is an entropy gradient, there is a direction of time. Wherever entropy reaches its maximum, Every process stops. Change no longer has a preferred direction. The arrow of time does not reside in each collision, each airflow, each photon, each equation. It resides in the imbalance of the universe, in the special distribution of entropy. And if even a simple machine like the ratchet is forced to obey this truth, then you can imagine all the time we experience exists, only because the universe did not originally choose the equilibrium point. So why does our brain only remember the past and cannot remember the future? This is not some spiritual mystery, not something mystical lying beyond science. It is the direct consequence of the very principle that has guided this entire journey. Increasing entropy. Your brain is a physical device, operating through ultra-complex electrochemical processes in neural networks. When you form a memory, like remembering that you sat in this chair, heard this sound, or read a certain passage, your brain creates a new ordered structure. Synapses are strengthened. Activity patterns are shaped. Protein molecules are rearranged into a more organized form. In other words, remembering is a process of locally decreasing entropy in the brain. But here is the paradox. You can only decrease entropy locally by increasing total entropy. To build a memory, your body must expend energy, burn glucose, release heat, generate electrical activity. The entire process increases the entropy of the surroundings. That is why memory can only form in the direction of time, where entropy increases. You cannot create a memory of the future, because that would require your brain to organize itself into a pattern that has not yet occurred, a pattern that depends on information that does not yet exist in any physical state of the system. Memory cannot precede the event, because the event is what creates the arrangement that becomes the memory. Imagine you are watching a television show. You can only record a scene after it has played. Why? Because to record it, the system must receive information from the actual event, and that information does not exist before the event happens. The brain works the same way. It does not prophesy. It only reacts. The past leaves physical traces, sound waves, vibrate your eardrum, photons, activate retinal cells, molecules, interact with neural receptors. The future does not. It has not yet touched you, and because it has not yet impacted any physical structure in your brain, you cannot store it. Once a memory is formed, it clings to the neural structure, a structure with lower entropy than the possible disordered state. But to maintain that memory, your body must continuously exchange energy, continuously release heat, continuously push the entropy of the environment higher. You see, memory only exists in a universe where entropy increases. If entropy did not increase, if there were no gradient, no direction, no difference to exploit, there would be no way to build structure. The brain can only record what happens while the world is moving from its initial order toward greater disorder. And that is why human psychology experiences time in one direction, the direction in which entropy increases. This is what physicists call the psychological arrow of time. It is not independent of the thermodynamic arrow. It depends entirely on it. The thermodynamic arrow creates the conditions for memory to form. The psychological arrow is simply its copy inside the brain. I want you to picture this with a familiar example. You strike a match, the flame ignites, heat radiates into the environment. Surrounding air molecules are excited. Light hits your retina. At that moment, your brain records the image of the burning match, thanks to countless physical changes. But you cannot record the image of the match before it was lit, because before the flame appeared, there was no physical signal for your brain to process, no photons emitted, no heat released, no molecules changing trajectory, no data, no physical basis for a memory of the future. Psychological time is not one way, because our consciousness wants it to be. It is one way because every process that creates memory depends on a flow of physical information that only moves in the direction of increasing entropy. Entropy does not only determine the diffusion of ink in water, the shattering of a glass, the expansion of gas. It also determines how we perceive the very flow of time itself. You can only remember the past because that is where the world leaves clear physical traces in your structure. You cannot remember the future because it has not yet created any physical trace. In other words, the future leaves no signal for you to remember. The past does. And if the brain can only record the past because entropy increases, then the truth is far larger still. The entire universe is a gigantic notebook recording everything that has ever happened, not in a romantic or vaguely metaphorical sense, but in the literal physical sense, the informational sense, the sense of what the fundamental laws force nature to do. Every stone, every breeze, every photon, every air molecule around you carries traces of what happened before. You simply do not notice because those traces are too subtle, too dispersed, too hard to read, but nothing that ever happened completely vanishes. Sandstone is a perfect example. When you look at the layered rock in a cliff face, you are looking at millions of years of the past written in strata, thick layers, thin layers, pale layers, dark layers, each layer a climate state, a flood, a windy season, a geological epoch. No one deliberately recorded it. Entropy did, because as sediment settled, it arranged itself according to the prevailing environmental conditions. A new layer does not deny the old. It simply overlays it, transforms it, but still preserves information. Now look up at the sky and think about the cosmic microwave background, the CMB, the oldest radiation we can measure, emitted just 380,000 years after the Big Bang. It is light from the infancy of the universe, stretched over billions of years by the expansion of space-time. Every tiny fluctuation in the CMB, even 1 part in 100,000, is a line of writing in the universe's diary, recounting what happened when matter had not yet separated from radiation. Those minuscule ripples became the seeds for galaxies, stars, planets. When you look at a CMB map, you are not just looking at the sky. You are looking at the very ancient origin of every structure you know, including yourself. You see, the 14-billion-year-old universe has not forgotten its past. It recounts its past through stardust, through cracks in rock faces, through light bent by distant galaxies, through radioactive isotopes buried deep in the earth, through the large-scale distribution patterns of galaxies we observe in massive surveys like SDSS or DS. Every photon your eyes see has traveled thousands, millions, even billions of years to reach you. When you look at a star, you are looking into its past. When you look at light from a galaxy 2.5 million light years away, like Andromeda, you are looking at the moment it emitted that light. When human beings did not yet exist, time there is not just a concept. It becomes matter, becomes image, becomes data. You can measure, analyze, plot on graphs. Think of something more ordinary, the dust in your room. It sounds completely mundane, but it too is a diary of time. Dust carries fragments of skin, fabric, pollen, ash, pollution. It is the microscopic history of the space you live in, written by entropy. Imagine you seal a room for 50 years and let no one enter. After half a century, we could read back what happened in that room, how humidity changed, how long sunlight entered, how wood expanded and contracted. Everything writes into everything else. Even Earth's atmosphere is a notebook of the past. Carbon 14, nitrogen 15, oxygen 18. Isotope ratios tell of storms, volcanic eruptions, how much CO4 trees absorbed. When we study Antarctic ice cores, each ice layer is a year. Each trapped air bubble, a perfectly preserved sample of ancient atmosphere. The universe never stops recording. The way the universe records is not like the way humans write diaries. It is more like throwing a stone into a lake. Ripples spread, reflect, interfere, affect every water molecule. Each molecule hits the next, transmitting information from the original throw. Those ripples never completely disappear. They simply spread until they become so faint the human eye no longer notices. The past is always there, in the microscopic configuration of reality, but dissolved into an ever-expanding ocean of entropy. And this is what I want you to feel deeply. Entropy is not the destroyer of the past. Entropy is what turns the past into the memory of the universe. If entropy were zero, every state would be stable, unchanging, without imprint. No history, no evolution, no story. But increasing entropy creates layers, scars, traces, from sedimentary rock to the cosmic microwave background, from stellar ash to fossilized footprints of ancient creatures. The universe, through its own increasing disorder, has recorded its own story. Every physical system is a page. Every photon is a letter. Every dust particle is a comma. And we can only read a very small part of it. If the universe is a gigantic notebook containing every trace of everything that has ever happened, then the next question is not just how does that work, but what does that mean for the way we see reality? And this, for me, is the most beautiful part of the story. Because from cold equations, from entropy, from probability, from quantum mechanics, and the strange distortions of space-time, we arrive at a conclusion so familiar that humans often overlook it. Time does not merely pass. It engraves its story into the very structure of the world. Every ray of light you see is a fragment of the universe's memory. Every dust particle you touch is a small chapter of Earth's history. Every carbon atom in your body once resided in the core of a star that died billions of years ago. We do not merely live in the universe. We are products of the past, rewritten countless times. The meaning of information never disappearing does not lie in the possibility of going back in time, because we cannot, but in understanding that the present is the direct physical inheritance of the past. Not a metaphor, not a thin philosophy, but a mathematical truth. Today's state of the universe exists only because it is the result of previous states, encoded, dispersed, mixed, but never erased. And this changes how we understand ourselves. It says that every moment we live is built on the foundation of countless events that happened before, too many for the mind to imagine molecular collisions in water, 500 million years ago, that drove the evolution of fish, a supernova explosion 7 billion years ago that released heavy elements to form our planet, the temperature and density of the early universe that determined the formation of the Milky Way, our home. All those events left traces, and the universe carries them like an unerasable memory. For me, this is where physics becomes more like art than mathematics, because understanding that the past does not disappear brings a kind of indescribable beauty. The beauty of continuity, of structure, of connection. It makes us realize that the world is not a series of disconnected moments. It is a tightly woven network of history. The echoes of the Big Bang are still here in the form of the cosmic microwave background. The deaths of stars are still here in the carbon in your blood. The initial motions of matter are still here in the distribution of galaxies. Even the stream of thought you are having right now, this very moment, is the result of countless uncountable events, memories you have stored, environmental stimuli you have experienced, decisions you have made, and all of it is the story of entropy, information spreading, diffusing, mixing, becoming the foundation for what comes next. This makes one thing very clear to me, something I have always believed. Understanding the universe does not make the world more boring. It makes the world more beautiful, because when you know that every photon you see is a piece of the past, you begin to look at light differently. When you know that every atom once belonged to something else, you begin to look at matter differently. When you know that nothing ever disappears, you begin to understand that the present is a wonder, a single configuration among trillions upon trillions of possibilities created by the entire history of nature. There is something I love telling my students. Physics does not teach you how to change the world. It teaches you how to look at the world in a way that changes it. And here the realization of the indestructibility of information is one of the greatest changes. It helps us see time, not as a river that flows away and vanishes, but as a symphony in development, where every previous note still resonates, blending into the notes that follow. You cannot hear each note individually again, but the entire melody is still there, providing the context for the present moment. And now, when we have traveled this long journey, from the falling glass in the opening section to the subtlety of cosmic entropy, from reversible molecular collisions to Hawking radiation emitted from black holes, from the way the brain stores memory to the way the entire universe preserves its own footprints, we can look back and say one simple but powerful thing. The arrow of time does not come from the laws of nature. It comes from the very initial circumstance that the universe chose to begin its story. The fundamental laws, the deepest laws of physics, do not require time to flow in one direction. Newton does not require it. Maxwell does not require it. Schrödinger does not require it. Even Einstein, when writing his field equations, did not say that time must run from left to right instead of right to left. Not a single equation says that a falling glass must shatter, or that a drop of ink must spread in water, or that a flame must radiate heat into the environment. All of those things could, in principle, run backward according to the laws. But the universe does not run backward. It runs in one direction. It began in an extremely ordered state, extremely improbable, and since then, entropy can only increase, causing everything you see, touch, and experience to move in the direction of expanding possibilities, never narrowing them again. And that is exactly what ensures the glass never reassembles itself. When it shatters, its information spreads into trillions upon trillions of microstates around it, in the air, in vibrations, in fragments, in light. None of that is lost, but it is dispersed to the point that no brain, no computer, no power can ever put it back together. The past does not disappear. It is hidden in disorder. The future is not pre-written. It is the outcome of trillions of microscopic events that have not yet happened. And we stand between those two realms. One that has diffused so thoroughly it cannot be returned to, and one that is not yet determined, but is constrained by the very direction that entropy has drawn. A skeptic might ask, if we cannot access the past, what does it mean that it exists in microstates? I think it means the world is far more interesting than you imagine, and you cannot make it less interesting by complaining. The world is interesting because it is not a temporary stage. It is the consequence of beautiful rules, of which every day you live is an example. Those rules say no information ever disappears, but a great deal of information becomes useless to you. No past is ever erased, but a great deal of the past you cannot read. No future is written in advance, but a great many futures are constrained by the initial conditions of the universe. And when you understand this, you do not merely see time as one way. You see it as a direction of freedom, the direction in which the world can create, evolve, expand, give birth to stars, planets, life, consciousness, and ultimately to you, sitting here listening to this story. When I teach physics, I always tell my students that our task is not to solve every mystery, but to learn to love the beauty of the mysteries that remain. And few mysteries are more beautiful than this question. Why does time only flow in one direction? We know many parts of the answer: entropy, probability, initial conditions, the unitarity of quantum mechanics, but we do not know everything. And that is exactly what keeps the universe from being boring. In fact, That is precisely why physics is interesting enough to be worth living for. Do not be sad that you cannot go back to the past. Be glad that you are living in a universe where the past worked hard to create you and still has enough disorder left to surprise you in the future. And that truly is the greatest gift of the arrow of time. If you love journeys of discovery like this one, please hit subscribe so you can join me on the next adventures. See you in the next lecture, where we will once again open different doors into the nature of reality.